So it looks like, can everyone see the slides?
Yes.
Yep.
Great.
Yes.
Okay. Carla, can you see the slides?
I can see the slides.
Okay. Well, without further ado, I guess let's get going. And I suppose you'll just have to ask Kip to advance.
Okay.
No, actually, I'm projecting the slides.
Oh, it's Paul. Okay. Well,
Yeah.
Perfect.
Sorry. Perfect.
And hopefully we can make it past slide 1.
Thank you all for your patience. Without further ado, Paul and Carla.
Well, thanks, everyone. I only know Carla on the calls, so I'll introduce myself. I'm Paul Nicholas. I'm the Chief Scientist of the Large Scale Analytic Systems Group at Johns Hopkins Applied Physics Lab. My background, I worked under Carla as a PhD student in the Systems Engineering and Operations Research Department at George Mason. Also a prior Marine, so did my master's degree at the Naval Postgraduate School. In the Marine Corps, I was a communications officer, so worked a lot with tactical radios and spectrum allocation, and that's where my interest in this topic came from. So, Carla, I don't know if you wanted to do a short introduction.
Sure. I'm Carla Hoffman. I'm a professor of operations research and systems engineering at George Mason University. My interests are combinatorial optimization and solving important, hard optimization problems. And Paul brought this wonderful problem to my attention, and we've been having fun working on this problem ever since. And just to explain, Caleb Fry, it was an intern both at Johns Hopkins University APL Lab for the summer, last summer, and then over the Christmas break. And he's been helping us just do some coding and visualizations.
Great, thanks. And if there's any questions, please go ahead and shoot them when you've got them. I won't be able to see any chat or anything here when I'm in presentation mode, but please just stop me at any time. So our motivation here, our background, like I said, related to my experience in the Marine Corps, and even now more so in the last few years, our military forces, specifically our tactical ground forces, are very dependent on the ability to transmit digital information rapidly. This is highly dependent on the availability of RF spectrum. And unfortunately, we just can't go get more of that. It's becoming increasingly crowded. So lots of additional civilian devices out there. It's very easy to get jammers and further occupy that spectrum. And here in the United States, the FCC is actually absorbing a lot of the spectrum that was previously allocated to the military for these types of operations. And Carla is highly involved in the FCC spectrum auction, which is a related but completely different and much larger effort there. Different talk, but a lot of synergies between these two projects. So we've got this scarce spectrum available. We want to be able to allocate it to these ground forces so that they can use it to the best of their abilities. The ability to reuse these channels is primarily limited by the co-channel interference that they receive. So that is the interference from other units, other tactical military organizations that are trying to operate on the same channel, but have different communications needs. Also, some additional challenges to this problem, which make it really exciting, go beyond kind of the academic literature, which is typically focused on kind of tabletop type terrain. We consider the implications of movement, mobility, the actual radios moving over time, as well as rough terrain, which makes things highly nonlinear. So current methods of doing this, which I did as an active duty officer, include planning tools such as SPEED and Spectrum 21. These are a little bit more advanced than simply drawing circles on a map and trying to determine your radio coverage boundaries, but really not much more than that. They don't get into considerations of jamming, and certainly not considerations of how you plan larger multi-radio networks. So we are very interested in these challenges faced by spectrum managers. How do they make do with the spectrum that they have available? questions that we've looked at in our previous research include trying to minimize the number of channels needed, trying to minimize channel changes over time. So once you have these assignments and your military forces are now actually conducting an operation, how do we keep them from flip-flopping back and forth on their radios? And then given the scarcity of spectrum, how do we minimize interference in a contested environment, which we know is going to become increasingly prevalent when you're in a near-peer adversary type situation, or even if you're operating in an area with just lots of traffic and people are unintentionally interfering with you. We're focusing specifically on tactical mobile ad hoc network, or MANA radios, but there's a broad applicability here with any sort of RF device that assigns a discrete channel to a radio. So we're not talking cognitive radios. Most of the handheld and man-portable radios used in the Marine Corps and the Army, you still have to set a specific channel for them. And we use realistic full-size scenarios, actually based on Marine Corps planning scenarios. So our overall approach to all of these problems has been to model them as 0-1 integer programs. In the previous research, we looked at minimizing the number of required channels and minimizing those required channel changes. So I'll talk about those first two challenges and where we got with our initial research. And then Carla's going to get into how we start looking at the impacts of the adversary and the effects of additional jamming. So we used a simulation tool called TIREM and Satellite Toolkit, now called Systems Toolkit, to actually instantiate our defense planning scenarios. We took actual scenarios which are classified, but moved them over into the unclassified realm, such that we could then talk about it on forums like this, and we have all that simulation data available to us. Actually, we've made it publicly available too. We set it up on a GitHub site. So our model of MANA operations, we're looking at discrete units of the military. So it could be a platoon or a battalion of Marines that needs to communicate. They have their own communications needs. Within that unit, there could be up to 30 radios. These could be handheld or man-portable radios, or even radios mounted in a vehicle. So among that unit, those folks, those radios need to communicate, but they don't need to communicate with other units. There might be some sort of backhaul network that we're assuming is available for that type of communication. So any two units here indicated in red and green, or blue and green, that are on the same channel but are not part of the same unit are candidates for causing co-channel interference. So every radio could interfere with every other radio in the worst possible case. So kind of indicated here by those gray dashed lines, instead of just looking at interference between any two radios, we actually look at cumulative co-channel interference, which is another thing that differentiates our approach from most of the research. So our data set's a little bit more detail here. Office of Naval Research will be very familiar with the term MAGTAF, Marine Air Ground Task Force. So we initially looked at scenarios involving Marine expeditionary units and brigades, but found that we could solve these scenarios quite easily with existing methods, and we wanted something really hard. So we went with the MEF, the Marine Expeditionary Force, up to 60,000 Marines. Our scenario has 118 units comprising 1,887 radios, and this was not easily solved with existing methods, luckily for us. So a couple of the formulations that we started with, the MOCAP is trying to minimize the number of channels, and the minimum cost channel assignment problem over time is trying to minimize those required channel changes once you have that MOCAP solution. So that was part of our initial research that we conducted, and then our new research that we're discussing in the second half of this talk is focused on that third problem, the minimum interference problem. So kind of think of this almost in phases of operation. So when you're going into a new operation, your spectrum manager in advance is going to try to plan out, try to figure out how much spectrum his or her forces requires. So they want to solve this first problem, this minimum order channel assignment problem. So what's the minimum number of channels they need to be able to operate in the expected environment? Once you have those channel assignments out there and your forces are operating, you want to have some sort of channel plan. So as they progress, the particular scenario you're looking at involves an expeditionary assault, an amphibious assault. These forces are generally moving from the sea northward and spreading out. So as they do that, you want to have some sort of plan that tells them how to change channels. You don't want them flip-flopping back and forth every few hours or every few days. You want to have some plan that considers that movement, that change over time. So that's the second problem. And the latest problem is, of course, in a realistic environment, you're going to get jammed. And even if you don't get jammed, you're still not going to have enough spectrum to go around. It doesn't really matter what you ask for. In step one, I can guarantee you're not going to get what you ask for. Higher headquarters is not going to magically come up with more spectrum for you. So at the very least, you need to minimize this co-channel interference among your own units, and you also need to perhaps consider the effects of additional interference. So our first problem, we looked at, again, modeled all these programs as integer optimization problems. My initial pre-PhD attempt was just throw it at Cplex and a really big computer cluster and see what happens, because I had a cluster, right? So if you have an enormous computer cluster, of course you want to throw the biggest problem you can find at it. So 14 very large desktop computers resulted in absolutely no progress over 2 weeks. The only thing I had to show for that was a melted UPS battery in one of the backup power supplies, which is kind of cool. It was kind of cool to see the actual melted battery, but I didn't even have a feasible solution at the end of that 2 week period. So the problem was certainly more difficult and required a little bit more nuanced approach. So over the couple of years, the research that Carla and I did, we looked at adding in things like lazy constraints, so we didn't consider the entire problem at once, and the maximum clique to which actually really helped because Cplex itself wasn't able to leverage that in terms of pairwise interference. It helped us get to good solutions much faster, and sometimes in the order of seconds. And we used constraint programming in a hybrid approach to quickly provide a lower bound on the number of channels required. So in pictures here, on the left-hand side, actually in both of these depictions, we have in the horizontal axis the time steps that we looked at in this scenario. So we broke it up into 20 different moments in time during this amphibious assault. On the left-hand side, we have the objective values. So we're trying to minimize the number of channels here. Down is good.
Hey,
our heuristic. Is there a question?
Hey, sorry to interrupt. Yeah,
Yes,
this
please.
is Matthew Gombley from Georgia Tech. I just had I was hoping to ask you a question about the different modeling facets you tried. Did you also try employing set of set constraints or looking at Binder's decomposition techniques?
So our lazy constraint project or approach is a generalized method of Bender's. So I think essentially that's what we're doing with the lazy constraints.
Okay, cool.
So we started with a kind of a simple packing heuristic just to get a sense of how hard the problem was. You see that in orange. And then gradually added sophistication to our implementation of Cplex. So starting with Cplex itself, then adding maximum clique to it, as well as Bender's decomposition, the lazy constraints. You can see we had a very nice improvement there. And then using CP, we were able to provide that lower bound. We were able to find infeasible solutions within less than a second. So that is to say, we knew, because of the problem is discrete, that we needed at least one more channel for the problem to be feasible. And we could find that very quickly. What was very interesting and kind of symptomatic of constraint programming in general is if you gave it one more channel such that it should be feasible, it would take a really long time to find anything at all. So kind of a complement here between the optimization focus of the traditional Cplex branch and bound algorithm and the CP solver, which is approaching from the feasibility aspect of it. So the little black hash marks there on the left-hand side provide your lower bound, which in almost all cases was within one, which is basically showing the lower bound for our Cplex approach. And then the right-hand side, just the indication of the run times required to achieve these results. Our heuristic's still fast, but even in an operational planning scenario where you're not yet ashore, you're not yet actually conducting operations, we think these run times are reasonable. Certainly better than 2 weeks. And then that second problem I mentioned, we're interested now, once we're ashore, once we have the solutions to that mocap problem, we want to make sure our operators aren't needing to flip-flop channels back and forth. And a naive way of approaching this is just to assign units to the channels as they appear. So just an ordered list. So unit 1 gets the first channel, unit 2 gets the second channel, and so on. This produces surprisingly bad answers, right? In fact, we see a lot of that flip-flopping behavior because one channel is exactly the same as another. The solver doesn't know any better. One of the novelties in our previous work was identifying within this larger problem optimal substructure. That is, we can break apart solving these problems and changing channels over time and solve each one of these separately using an assignment problem, like the classic assignment problem, which can be solved in polynomial time. So in fact, we can solve this problem very quickly without need for anything like Cplex. So in a very cartoonish form here, at each time step, we're solving each problem separately and looking at the penalty that you get when you are required to change a channel. In this case, we decided units with lots of radios that require lots of up to 30 people to actually manually change those channels. That's worse than if you have a unit with only 4 radios. So we're trying to minimize that overall channel changing exercise over time at each time step by breaking it down separately, such as this, and then going back and finding kind of the thread going through this network structure that you see here. We can solve this problem very quickly in polynomial time. So that naive, so comparison of the results here, the naive method in orange, that's just assigning channel 1 to unit 1, which is not such a great idea. And then our exact method, which is provably optimal, assuming that you come in with the optimal solutions to the MOCAP or minimum order problem. We saw a 34% reduction over the course of those 20 time steps. So provably optimal, and we get that entire thing solved in 53 seconds. So we're really excited about that result. What I call the horse blanket graphic here. I kind of like some of the qualitative results as well. So here is a way of looking at, quote, the goodness of this solution. So this naive method, we're seeing this as bad because here, white here in this image indicates that you don't require a channel change. So the bigger units are up here. So this is sorted top to bottom by the largest units up here. So up to 30 units are required. And then down here are some of our smaller units. They actually get down to 4 radios per unit. Those are tank battalions. A tank platoon is only 4 tanks. So this is particularly painful to us when we see all of these radios needing to be changed in very large units. What we'd really like to see are these big, long white streaks where you can go time step after time step without needing to change channel, again, indicated just by the white block. So there's our naive method. And our exact method, 34% reduction there. You see a lot more white in general. You see a lot of white toward the top of the screen, indicating that it is favoring those larger units with more radios, and kind of the longer white streaks that we'd really like to see, which indicates that, in fact, they are going more than one time step without needing to change their channel. Okay, and I think this is where I turn it over to Carla.
Okay, well, what you've heard from Paul, I think, is something that is really useful to think about in almost any difficult combinatorial optimization problem, which is using hybrid approaches. As we all know, the way we solve these problems is by having the lower bound and the upper bound converge to a single value. And I will say this, and then I'll highlight it at the end. You can't expect a general purpose code like Cplex or like Gurobi to be able to know what you know about your problem, and what you know about your problem is probably going to be able to assist Cplex or Gurobi in getting the job done. So our current challenge is how to quickly recover from interference that is likely to come from an enemy attack, namely jamming. And we assume that we're going to begin with the feasible solution, namely the assignments that each of these units received before the jamming. And we're going to assume that that everybody on the battlefield, all of the units, know this original assignment. We're also going to start with the simplest case, which is that we only have one source of interference. It's localized to one unit and one channel. We have no spare channels available, namely since we started with the feasible assignment that had been given to each of these units. Remember that feasible assignment used the minimum number of channels that it was possible to use. But we do make another assumption, and that is that we think that two units that couldn't be assigned the same channel because of friendly interference would also be impacted by this jamming experience. So neighbors of the jammed channel can also not use that jammed channel. And as I said, a neighbor's unit that could not be assigned the same channel as the jammed unit without causing some radios to lose communication. So if you're thinking about the battlefield, you have a collection of units that are spread out throughout the battlefield. We can create what we call an interference graph, whereby we know what radios can't be assigned the same channel. Next slide. And so our question is, how do we reassign channels to minimize impact of jamming without running a global optimization over all radios? This is an important characteristic. We know that it is hard. We are assuming that one can only communicate with these neighbors, namely the units that were close enough so they couldn't be assigned the same channel. And what we don't want to have happen is a unit to just react and change its channel without having any consideration of what that's going to do to its neighbors. Then the neighbors change their channels, and we have this sort of chaotic behavior that, if you thought about agent-based modeling, might converge, but it's going to converge slowly. And that's a dangerous situation to be in when communication is so important. So the question is, can we do this only through local communications? And can we change as few units, channel assignments as is possible? Okay, next slide now. So what is our technical approach? We develop a constraint programming approach to quickly repair the network following a localized interference event. Next. All I need, you're right. And how do we do this? First of all, we're going to relax the hard constraints. Here, there are two ideas coupled in this. One is that the problem is simply too hard to try to think about the entire battlefield situation. And besides, we don't want to have units trying to get information from their neighbors, and then information from their neighbors' neighbors, and then information from their neighbors' neighbors' neighbors. What we do want to do is solve very quickly a relaxed problem, relaxing some of these interference constraints, and then trying to improve the solution we get when we have created a problem that's simple to solve in a very short period of time. Next, can I have the next bullet? So we want to keep the overall allocation theme as consistent as possible within the initial solution. We really want to keep the solution as good as possible. Yeah, Paul, if you wanted to do all of these, you could. So we want to only consider local neighborhood of units. And so what's the smallest local neighborhood? Just that single unit. And if we can find that because of the way this part of the battlefield is configured, there is a new channel for this single unit without interfering with anybody else close to them, it just changes and we're done. But if that's not true, we're going to then expand the neighborhood. Namely, it's going to be all of the units that would have pairwise interference with this unit if they were both on the same channel. Any unit that is outside of what we are defining as a neighborhood is forced to remain on its existing channel assignments. And what that means is those units are not impacted by this new channel assignment if we can find such a feasible assignment. And we iteratively attempt to solve, increase the size of a local neighborhood when necessary. And I should say that to make the problem simple enough for constraint programming approach to work, we are only considering pairwise interference in the feasibility checking and our optimization. But on the other hand, when we're done, we're going to evaluate how well we did, not only by pairwise interference, but on the cumulative interference. So if a radio is receiving interference from multiple other radios and possibly the jamming activity, all of that is summed up. And if it violates this threshold, or this communication threshold, then it's counted as a radio that cannot communicate. So there's some anomaly between optimizing for one thing and then judging it against something else. But that something else is truly what we care about, which is that radios can communicate. Okay, next slide. So how does this work? First of all, we use constraint programming to check the feasibility of an assignment very quickly. This always took less than 1/10 of a second, no matter how large we expanded the neighborhood. It could say yes or no definitively as to whether or not there was a feasible assignment. Then we use the CP optimization, constraint programming optimization, to improve the feasible solution. Now we're going to attempt to minimize the number of radios that receive excessive interference, but the optimization is using only pairwise interference for this calculation. Once we have found a neighborhood for which there is a feasible solution, we do not consider increasing the neighborhood. We simply try to find the best solution for the where we know a feasible solution exists. And as our test set for this, we run each time set, of which there are 20, and each unit, of which there are 118, individually, so that we are jamming every radio in every unit in every time period. And that ends up with 2,360 instances to test. We compare our local neighborhood method to a global constraint programming optimization. And what I mean by that is, remember I said any units that were outside of the neighborhood were fixed to their prior channel assignments. In the global case, we say all units can receive new channel assignments. But the interference graph, the arc structure, remains the same as for the local neighborhood method. And we give the global optimization method 500 seconds on a large 48-core server with 768 gigabytes of RAM. And what we're really saying is that's not feasible for the battlefield, that we wouldn't know everything there is to know about these units, and we wouldn't have every unit would not have that kind of computation power. On the other hand, we are assuming that every unit would have a standard issue laptop. So that's what the local neighborhood method is using for all of our tests. Next slide. So here's our results for our first local neighborhood attempt. One of the things you will notice is the orange is the local neighborhood heuristic, and it's doing pretty well. It's even doing better than giving 500 seconds on this really heavy-duty machine and seeing the whole network. But you'll see that there are 4 spikes. And those spikes are really not acceptable. Having close to 90 radios, which is what the spike look of the one all the way to the left on this slide is simply unacceptable. This would be the case where the other radios would then start to change their channels, and then because of their changes, it's conceivable that some other unit will start changing their radio's channels, and we could have chaos. So we looked carefully at what was happening on each of these 4 cases, as well as comparing the global optimization solution to the local. And we found a very important consideration, which was that the global optimization was changing more channels, more units were having their channels changed than was true in the local. And for these 4 spikes of the local, lots of channels were changed. So, next slide. The first optimization just tried to minimize the total number of radios for unit J receiving excessive interference. And what we realized was we really needed another term in our optimization to penalize moves to new channels. And the question was, if we added this new term, would we get an overall better solution? So instead of just having P1 of J for all J units, we have P2 of J, which says that whether or not unit J's channel assignment has been changed. Next slide. So now, first of all, realize that the scale is different. It's still the number of radios receiving excess interference, but now we only go up to a possible 14. And in truth, this solution, the worst case, only has 12 radios receiving excess interference. And you will also notice that now the global optimization is doing far better than the local optimization. And in truth, I'm now getting I am getting feedback. Are you hearing the feedback?
I'm afraid
Yes,
we
I'm
are.
hearing the feedback.
Yes.
I'm not sure what to do about this. It went away. Good. Back to normal. Okay, so if you'll notice on the blue, the greatest number of radios receiving excess interference is 4. Now, these results are based on our first approach, which said we really needed this done quickly. We wanted to see if that was possible. And we set hard constraint J equal to 4. What does that mean? That means we only put an arc in the interference graph. We always enforce the constraint that said 2 units could not be on the same channel if 4 or more radios would receive excess interference. And so now suddenly this was looking good enough for us to ask the question, what happens if we gave it a little more time or put more restrictions in the constraint set? How much could we, because the neighborhood search was finding feasible solutions that weren't looking over the entire battlefield? Could we make the problem somewhat harder and get better results? Next slide. So we were actually asking two separate questions. If we put more arcs in the interference graph, which is to say put more constraints into the constraint programming problem, would we get better results? And since there is this relationship between solve times and the number of constraints in the interference graph, what would happen if we gave the optimizer more time? And our test said, well, we gave it 10 seconds. And in truth, the 10 seconds was because they were all solved within, add hard constraint J equal 4. They all solved within 10 seconds. But now if we're going to make the problem harder, would 20, 30, 60, 120 seconds work? And here are our results. If you see hard constraint 4, the average solution time is about a second, 1/100th of a second. If you look at hard constraint 3, you can see that it isn't solving all the problems, which is why when you give it more time, it keeps working at trying to solve the problem. And the average time for hard constraint 2, which has the most constraints of all our testing, took, on average, not much time, about 7 seconds. But there were problems there were instances where it took up to the whole 120-second time limit. What about the average radios receiving interference? Well, if you look at hard constraint 4, the average radios is 2.6 because it solved them all to determined optimality in that time. On the other hand, the time limit, the average radios receiving excess interference for hard constraint 2, the average radios went down to 1.57. And the max, but it's also interesting to look at the maximum radios receiving interference, and this sort of shows you that these really are heuristics. Hard constraint 3 works better than hard constraint 2, and even hard constraint 4 works better in terms of the maximum number of radios receiving excess interference. So it's not perfect, but it seems to imply that we really want the number of radios receiving excess interference to be as small as possible. And so it seems as if hard constraint 2 with a time limit of 60 is about as good as we can possibly get on average. Next slide. And so what this does is show hard constraint J equal 2 with varying time limits. And if you look across this, and so the across the horizontal axis is the number of radios receiving excess interference. And this is just a histogram of how many receive, how many of these times do you get 0 interference? Do you get 1 radio receiving, 2 radios receiving, 3 radios receiving, etc.? And the different bar colors show the different times in seconds. And one thing I will highlight is that blue of the 5 lines, the one to the right, the sort of medium blue color, is the global solution, giving it 500 seconds. And you can clearly see we still might be able to improve this. But for something that's only going to take 60 seconds, we're doing pretty well. And the reason I'm saying 60 seconds is if you look at the difference in the number of radios receiving excess interference, there really is virtually no difference between giving it 60 seconds and giving it 120 seconds. Next slide. The other thing I would like to show is just how many radios are receiving a smaller amount of interference, and this is shown in the same kind of histogram. And what you see is with hard constraint 2, which is the dark blue, far more radios are receiving either 0 or 1 radio receiving interference. So our conclusion is that this simplified problem, where mostly the battlefield is fixed in terms of the channel assignments that they had been assigned in the past that were optimal, and we only look at the units close to the jammed unit, and we work at first finding a feasible and then finding an optimal solution to a relaxed problem. When we compare it to the truth, which is how many radios are receiving interference in the aggregate, which is what this histogram is showing, it's really much, much better than we had hoped for. I mean, quite honestly, we were sort of happy with that first slide with the 4 peaks where things were looking pretty good in most of the battlefield, but pretty good was about an average of 3 radios, whereas this is really much, much better. Next slide. So, we have shown that our approach is inexpensive, where you're doing this on a single PC with C-Plex constraint programming solver. It's robust to many different battlefield and jamming alternatives. I think one of the great attributes of this is it requires little communication across the battlefield. And it converges quickly to a near optimal solution. And when I talk about near optimal, I'm saying if we know that there are a small number of radios receiving excess interference, this is a truth. It's not the 500. It's not comparing it to something that is also relaxed. We're just saying this is the number of radios, and it's really not very much. So what does our future work look like? Well, the obvious question, I think, is, will the same approach work for more intense jamming? And when multiple units are receiving jamming attacks, when they work individually and only with their neighbors, could they still obtain near optimal solutions? We think clearly that if the jamming is done if there's 2 units being jammed, but they're far away from each other, clearly these units can work independently without impacting much of the battlefield. But when does the interactions become too great, creating some sort of cascading problem? And in a cascading problem, is it going to converge quickly, or is it going to have a whack-a-mole effect, which is what we don't want? And if we find that there really are instances where things are not converging quickly, what metric should we use to identify those situations and try, at least in an overnight situation, reassign, as we did up front for the planning approach, a new channel assignment which works to keep as many units on their channel as existed, as close to what happened before, but possibly requiring truly a much harder optimization to be solved, which we know how to do. The argument for not doing it on a battlefield is quite simply that things are changing too quickly and you just want to maintain communication. I think I should end with going back to something I said I would end with. There is no slides on this, but it has been my experience working with Paul, as well as the experience with the FCC, that you cannot expect a general purpose solver to work as well as if this general purpose solver gets help, because the people modeling the problem know more about the problem. And what I mean by that is we knew that jamming has a geographic component to it. CFlex doesn't know where units are on a battlefield and can't necessarily understand that kind of change. When Paul talked about doing constraint programming, this idea of just having a feasibility solver ask the question, is this possible, means that from a vendor's decomposition perspective, you can increase, if you're maximizing, you can decrease the upper bound. If you're maximizing, and it's without these constraints, you are getting an objective function that's higher than it should be. Adding these constraints will lower the value of the objective function. These constraint program feasibility checks can be very, very inexpensive. The only thing CFlex or Gurobi does is do a random choice of some small set of variables to leave unfixed, fixing everything else and solving that small problem that it can do quickly. If it gets a better solution, it keeps it, and now it takes another random set and does it. Does the same thing. I think that we as applied optimizers can do much better than that because we understand the application that we're dealing with. And so I will end there. I will say that I hope Paul is as excited as I am about continuing this research, because I think it has lots of opportunities now that we have a mechanism to handle at least one jamming when some enemy jams a single unit. Now we have to look at the bigger problem of what happens if there really is intense jamming or multiple jamming on the battlefield. Thank you for listening, and Paul and I welcome any and all questions.
Thank you so much, Carla. Thank you, Paul. Does anybody have any questions for Carla or Paul?
I see a hand up.
I have a clarificatory question. Thanks very much for the talk. I assume that over time, the interference graph is changing. That's why we need to re-optimize. So I assume that the number of channels that you're using at every time step is the max over the time steps of the number of channels you need, right? So
it's different for each time step, so that if it was determined that you only needed a smaller number at, say, time step 6 than time step 7, we made the jamming problem hard for time step 6.
Got it. Okay. Yeah. So this is a question related to that. In the very first part, when Paul was talking about the assignment problem and then the change problem, would there be, I know a spectrum is very expensive, which is why you're trying to optimize it. Would there be a trade-off if you allowed one more channel than the optimum for the change problem? And what does that trade-off look like? Yeah, because that's related to this question I asked, because if you didn't make it as restricted as 6, because re-optimization is much easier even if you have a little bit of slack.
I think that's true. And it also begins to ask the question, if that channel were available, clearly you would want to do that. And you'd want to spread out the channel assignments so that anything that, you want to reduce sort of the threshold because you've got more channels. So you want to allow some new interference without it actually causing lack of communication. Paul keeps telling me there are less channels available than you need, but the reverse of that is the question of, if you don't have enough channels, what do you do? And I think the answer is you try to find a solution that has the minimum number of radios impacted. On the other hand, there's a secondary question that I also think is important. I think there is a difference between having one or two radios who were right at sort of that communication threshold barrier, finding that they can't communicate, versus having three of the four radios in a single unit no longer being able to communicate. And so there are a lot of alternative ways of looking at what could be problematic. But in that first case where there were 12 radios the maximum of 12 radios receiving interference, I wouldn't want 6 of them to be in the same unit.
Yeah. Thanks. I have a hard stop at 3, so I might drop off before all the questions. Thank you.
I know a lot of people have to leave by 3, but are there any other questions for Carla and Paul?
This is Matthew. Can you hear me okay?
Sure.
Okay, great. Yeah, thank you for your talk. My lab has had some good success in using graph neural networks to model these planning and scheduling problems. And we've used actually these neural networks to infer a way to sequentially construct initial warm start solutions for optimizers. And I know you talk about yes, there's certain key facets of C-Plex and Groby. One of the reasons why they're slow is because most of these solvers in practice, you have to develop good warm start heuristics and other assumptions, right, to kind of guide it to solutions. So I was interested to know, to what extent you played with machine learning at all, or other methods to try to help speed up with good warm starts.
Do you want to answer, Paul?
Yeah, we haven't on this project, but I'm involved in other work at APL where we are looking at that. Yeah, it's actually the direction of the technology is more going from this project to those projects to help them with their neural network approaches.
All right, thank you.
So I have a quick question. This is Chip Krebs from ONR. So how, on the practical side, how would you implement this capability? Is this going to be a tunable radio that in the background they would automatically be able to limit the channels or jump to another channel based upon interference or jamming? Or is this a centralized location at the mast where the comms officer is then communicating with each radio, indicating that you need to change the channel or something like that?
Yeah, it would be a distributed solution. So each radio or each node would be solving its own problem. And so a future challenge that we need to look at is how we prevent kind of these waves of changes kind of pushing back and forth across the battlefield. One nice way to start here is that we don't have that because of the way we kind of grow this local neighborhood solution. But if multiple areas are getting jammed at the same time, then we could possibly have those challenges. So, but yeah, the intention right now is that these units are independent and solving their own problem separately.
Great. Are there any other questions? Okay, well, I guess we can give a thank you to the speakers. I'm not sure how what the etiquette is, but thank you so much, Carla. Thank you, Paul. And Kip and I are going to be in touch about the next talk. This was really great. I'm recording all this, and I'll post this. I think I'm going to post it to YouTube actually, and so then I will send out the link to the talk as well as the slides. And just once again, thank you all so much for participating, and I look forward to seeing you guys again very soon.
Yeah, can I say thank you to you for having these talks? I think they're really valuable for the community as a whole who is trying to solve these problems.
Well, thank you. Great. Well, and thank Kip so much too, because he's a big push for all this as well.
Thanks.
Thank you.